I'm Mark Parsons, and I'm here to talk about the Exascale stand that we have at ISC this year. The stand represents 6 European projects that focus on the Exascale challenge, both the hardware and the software challenge. The first project I'm going to talk about is the project that I lead, which is the Cresta project. Cresta's interesting because it takes a view that the real challenge we have with Exascale is a software challenge. We don't ignore hardware. We understand that the Exascale machines will be incredibly complex, with complex memory hierarchies and many millions of parallel threads. But the real challenge we have, and which Cresta looks at, is what disruptive innovations do we need to do to make codes execute properly on an Exascale system. We've got 6 codes we're looking at, and they cover weather forecasting, fusion modeling, etc. And these codes are exactly the sort of codes that we'll have to run on Exascale computers. So having told you about Cresta, let's move on to Deep and Deeper and tell you about that project. So we're now at the Deep and Deeper projects part of the booth. These 2 projects focus on hardware and software co-design, whereas Cresta focuses entirely on software. The challenge of Exascale is twofold. We've got to deal with the application side, but we also have to build new and innovative hardware. And Deep and Deeper look at the challenge by bringing together 2 different types of parallel computer. On the one hand, you've got the traditional massively parallel computer. On the other hand, you've got accelerated computers, GPUs, or in this case, the Xeon Phi architecture from Intel. And Deep and Deeper exploring how to bring these 2 types of computer together to build an Exascale-ready architecture. So that's Deep and Deeper. We're going to move on now to the Mont Blanc project, which complements Deep and Deeper. One of the biggest challenges of Exascale computing is obviously managing the power budget that we have. Today's technologies would lead to parallel computers that had 500 megawatt power requirements, and we simply can't manage that. So the challenge is to see how we deal with energy efficiency, and that's really the focus of the Mont Blanc and the Mont Blanc 2 projects. These projects are taking traditional mobile technologies and deploying them for use as powerful supercomputing components in systems that can be built up from many of these processors to provide petascale performance and subsequently exascale performance. So Mont Blanc and Mont Blanc 2 have been looking at taking the Samsung ARM architecture, which is used in their mobile devices, and connecting them to network hardware, and then building massively parallel supercomputers from these components that fit within a very strict energy budget. At the same time, they've been looking at the whole applications and software environment needed for this, from the operating system to the tools to compile those programs, up to the applications themselves. So the final 3 projects I want to talk about are smaller projects which were funded after Deep, Mont Blanc and Cresta. And they're focusing on very specific aspects of Exascale. They're Epigram, Nemexis, and Exa'2CT. So these 3 projects focus much more on the programming side and programming model side of the Exascale challenge. Epigram looks at traditional programming models which are widely used today at the petascale, such as MPI, OpenMP, and the PGAS programming model, and looks at how they can be used at the Exascale. So can we take the best bits of each of these models and combine them to form a compelling, high-performance, highly scalable way of programming Exascale computers? Nemexis is a very interesting project because it looks at the industrial applications and the numerical methods required that we will require at the Exascale. So there are many challenges today on the industry use of supercomputing where it's already suffering from an inability to scale to thousands of cores. Nemexis looks at how we have to change our numerical methods in order to calculate some of the things we really want to calculate at much higher scales. And finally, the Exa'2CT program is looking at how you put together programming models and software architectures in order to tackle some of the biggest challenges we have at the exascale. So how do we design codes so that they properly execute at the exascale and so many millions of parallel threads? So here we are back at the Cresta project. I hope you've enjoyed finding out about the 6 European Exascale projects I've talked about. If you want to find out more, you can find out more at exascale-projects.eu, where there are links to all of the 6 projects I've talked about and lots more information. Thanks very much.
Thank you.